All right, the problem before us today, it says we have food and clothing that are shipped to survivors of a natural disaster. Each carton of food will feed 12 people, while each carton of clothing will help 5 people. Each of the 20 cubic foot boxes of food weighs 50 pounds, and each 10 cubic foot box of clothing weighs 20 pounds. The commercial carriers transporting the food and clothing are bound by the following constraints. The total weight per carrier cannot exceed 19,000 pounds. The total volume must be no more than 8,000 cubic feet. How many cartons of food and clothing should be sent with each plane shipment to maximize the number of people who can be helped? So this is our task. The first step is to make sure we understand what this question is asking us. So what is it they asked us to find? We often find that at the end of a long word problem, so it's always good to read through it once first and then to go back and kind of dissect the pieces. So right here it says we want to maximize the number of people who can be helped. That's what we're trying to find, the maximum number of people we can help. And to do that, we need to figure out how many cartons of food and how many cartons of clothing we should send to help those people. All right? The second part is to figure out what is it that we actually know. What pieces are we given in here? So if we look back, we're told several things. We're told how many people we can help with the food and clothing. We are told something about the weight involved. So we have 50 pounds for the food, and we have clothing that's 20 pounds. We are also given some information about the volume. Cubic feet would indicate the volume of the food, and here we're looking at the volume for the clothing boxes. We're also given some information about the plane that's carrying this to the survivors. We are told that we have a weight limit of 19,000 pounds. We cannot exceed that. That's important. And we're also told that we have a volume constraint here, that we can be no more than 8,000 cubic feet. So a lot of information in here. Quick summary, we know the weight and volume of the food and clothing that we're sending. We know how many people we can help with those items. And we know that we're trying to maximize that. We want to help as many people as we can. So our next step is to try to figure out a plan. What can we do with all of this information? And I find that when we have a lot of different types of numbers, it's helpful to kind of organize them. So let's look at organizing this. Food and clothing. And let's look at weight and volume. So for the food, we are told that each box weighs 50 pounds and takes up 20 cubic feet. And for the clothing, we are told that we have 20 pounds for each box and it takes up 10 cubic feet. Now, some of the other numbers that we were given up here. We were given some totals here, all right? Now, cannot exceed would be a maximum of 19,000 pounds. No more than is another way of saying we have a maximum of 8,000 cubic feet. So for our weight, we have a total limit of 19,000 pounds, and for our volume, we have 8,000 cubic feet. The last piece of information they gave us was information about who we can help. And it did say that we can feed 12 people with each box of food and 5 people with the clothing. All right, so lots of information here. This does resemble some questions that we've been using recently with systems of equations. So let's think about, could we solve this by creating a system? Since we have several different constraints, maybe having a graph would help us figure out where we could meet up all of these different requirements. So we've organized our information. We're going to consider setting up some equations or inequalities. We've also worked with those. And we can look at maybe looking at a graph of our information and then trying to figure out how we can meet all of the requirements. All right, so let's start working on that. So this is the information we had earlier. We also had number of people we can help. We had 12 for the food and 5 for the boxes of clothing. Now it is important to distinguish that. That is not a constraint. The plane has a limit of how much weight it can carry and how much volume it has to store the items. But the number of people we can help is not a constraint of the plane. That is actually going to what we have been calling our objective function. So if we think of the number of people we can help, for every box of food that we send, we can help 12 people. And for every box of clothing we send, we can help 5 people. So that information we're going to kind of hold off on. We need to figure out what values for X and Y, for number of boxes of food and number of boxes of clothing, we can actually take on the plane. So let's go back and look at some of these constraints. For our weight, we are told that each box of clothing weighs 50 pounds and each box of food weighs 50 pounds and each box of clothing weighs 20 pounds. And we are told that the plane cannot exceed 19,000 pounds. So we need to consider this as an inequality. We have to be strictly less than or equal to 19,000 pounds. We cannot go over that. For the volume constraint, we are told that we have a 20-pound volume cubic feet for each box of food, and we have 10 cubic feet volume for each box of clothing, and we have a maximum of 8,000 that we can put on the plane. Now, there's also one other thing that we know. We know that because these are describing boxes of things, we can't send a negative amount. So we also have the kind of implied constraints that X and Y can't be negative values. All right, so we have a system of constraints. We're going to look at where on our coordinate graph do we have values for X and Y that meet all of these, because we are given that all of these constraints exist. The bottom two constraints here, the implied ones, tell us that we are in quadrant 1. So we are going to limit this just to our quadrant 1. All right, and then to graph the other two constraints, since they are in standard form for our linear equation, we're going to go ahead and make a t-chart. Let's find our X and Y intercepts for each of those. So if we substitute 0 in for Y, we have 50x equaling 19,000, which would get us 380. And if we put a 0 in for X, meaning we take no food, just clothing, we could fit 950 boxes of clothing, just for the weight requirement. For the volume requirement, if we take no clothing, we can fit 400 boxes of food, and if we take no food, we could fit 800 boxes of clothing. So we need to look at how we can graph this information. Since we have some larger numbers, it seems reasonable to have our tick marks maybe go by 50s. My board is always off just a little bit. All right, so we had information here. Let's start with our red one. We had 380 for X and 950 for Y. I'm going to fix this a little bit here. So 100, 200, 300, 400, 500, 600, 700, 800, 900. 950 would be there. All right, let's go ahead and get a line in there. All right, getting our line here. All right, let's look at our inequality. We said that the 50x plus 20y has to be less than or equal to 19,000. So in terms of the points that fit that criteria, we would need to be underneath that red line, going towards the origin. For the blue one, we had intercepts of 400 for x and 800 for y. And getting that line in, all right, and the same thing with that one. We had to be underneath that 8,000 mark, so we would be shading below the blue line. So the part of our coordinate plane that matches all of our requirements, we need to be in quadrant 1, we need to be under 19,000 pounds and under 8,000 cubic feet, would be the section in here, and that's called that feasible region. So all the values in this region meet the constraints. But in our lessons earlier, we've talked about the fact that our maximums and minimums are always going to occur at a vertex. So let's go ahead and find the vertices of this region. Our first one, the easiest one there, would be the origin. The second one up here, sorry, my line looks like it's off a little bit here. Was the point 0800. We have a point right here. This was the red point that we graphed. We need to be underneath that red line. And that had the coordinates 380, 0. And our point where they intersect has the coordinates 300 and 200. Now, we've talked about this before. When we're finding that intersection point, it's always a good idea to double check that it truly is the point of intersection for that red and blue line. So we really should go through and put 300 and 200 in here for our x's and y's and make sure that we truly do get the 19,000 and the 8,000. Our other option is always to solve that as a system of equations, just those two, and find the point of intersection. All right, so now we have our vertices, and we knew that we had this objective function where we can help 12 people with each of our x's, our boxes of food, and 5 people with each of our y's, our boxes of clothing. And we wanted to maximize the number of people we could help. So we're going to go through our objective function and plug in our possible x and y values. But if we take no food and no clothing, we can't help anybody. If we take instead no food and all the clothing we can, which was 800, we can help 4,000 people. If we take 380 boxes of food and no boxes of clothing, we can help 4,560 people. And if we take 300 boxes of food and 200 boxes of clothing, we can help 4,600 people. So since we're trying to maximize the number of people we can help, this seems like our best option. So our conclusion would be we can help a maximum of 4,600 people by sending 300 boxes of food and 200 boxes of clothing. Now, it's always good to check to see if that's a reasonable answer. So again, we would go through all of our constraints and say, does this meet everything? Again, plugging in the 300 and 200, did we hit a maximum of 19,000 pounds? Yes. Did we hit a maximum of 8,000 cubic feet? Yes. We are within our quadrant 1. Our x and y's are greater than 0. And it makes sense that we want to try to get exactly to that 19,000, or again, as close as we can to those maximums, since we're trying to help the most number of people. We could certainly try some other points inside this region. But again, from our past experience, we know that the maximums are going to occur at the vertices. And since we've tested all the vertices, we can be confident in our answer. So we have checked it. The last thing that we want to do is think about what other extensions we could make with this question. We could look at other items that maybe need to be shipped. Maybe we want to add a constraint, add a requirement that we ship some medical kits. Or maybe we have a plane that can hold more cargo, and so our 19,000 and our 8,000 might change. That would change our graph, which would change our vertices, which again would change the number of people we could help. But there are some other things we could analyze and try to see what we could do to come up with a larger maximum of people that we could help.